Hello everyone, my name is Youssef Ammar Khouja. I would like to share with you cool formulas that I would like to call the new Euler's formula that I discovered back in 1988 while I was a high school student. I think they are not very important, but this is really a good exercise for high school students and it's also a good introduction to topology or graphs theory, for example. So let me recall the second most famous formula in the whole mathematics that was discovered by Euler in 1752, and it speaks about Archimedean convex solids. Like, for example, here we will use the most famous example, which is the cube, and it says that for any solid, convex Archimedean solid, the number of vertices minus number of edges, so vertices, they are all summits here. For the cube, we've got 8. So number of vertices minus number of edges plus number of faces, it always equals to 2. And this number here, it's named Euler's characteristic. Very important for topology and for many important studies at a higher level. So there is another version of Euler's formula for the polygons, for the flat shapes on the plane. So the number of vertices of a polygon here, for example this cross, minus number of edges, all the sides, plus number of faces here, 6, it always equals 1. Right, so I would like to prove something. Actually, the original question that I was asking myself about the cube back when I was in high school, how to cut the cube and get all the 11 different nets. Like, for example, this cross is only one of 11 different nets of the cube. I would like to show you the other different nets of the cube. For a moment, it's easy to check them on Google. So I aim to find out how to cut this cube to get the nets, and I discovered that the number you will have always to do 7 cuts for the cube to get those nets. So 7 cuts, like here, for example. Just imagine how you cut this cube. For example, let's say this is a cut. This is another cut. Actually, it's quite clear. You see, each time you cut an edge, you create. It's like opening one edge. When you open an edge, it creates another edge on the net. So this one is the cutted edge. This one as well. There's 4 corners, those 2 sides, and this bottom one as well. So 4 and 3, 7. So let's call C number of cutted edges. I'm writing edges with a capital E for a purpose. Edges from this solid, number of cutted edges from this solid into the net, into its net. There's another thing that we can notice when you get a flattened net like this. You have cutted edges, but the rest of the edges, like those ones in discontinued lines, they are folds. So they are edges that are not cut. So let's call them. It's good. It's always good to name things before going to any demonstration or proof. P is the number of non-cutted edges from the solid into its net. Or we can call P as well, or number of folds. So just bear in mind that each time I say folds means non-cutted edges. So I proved that C it always equals to V minus 1, number of vertices minus 1, and P, number of folds, always equals to number of faces minus 1. This is what I call a new Euler's formula, and I hope you will help to answer many questions about the nets of solids in general. And let's start right now to prove those ideas. By the way, we will also get to prove that the number of edges on the net, any net, it always equals to 2 times C. So this 14 actually it equals 2 times 7. 7 is the number of cuts on the cube. So V as well, we are going to prove that V equals 2 times C, 2C. And the other formula about the number of edges, we will find that the number of edges of the cube, it's easy to relate the number of edges of the cube straight away to its split net. What I call a split net means a net, or when you take all those faces from the cube and just take them as a component separately, you can see here that a number of vertices for the split net, V bar 24, E bar equals 24, and of course the number of faces always stays the same in the 3D, 2D, and the split version of the net. So V equals E, always equals E. This is very easy to understand because any polygon like this, for example, the number of vertices, so number V bar always equals to E bar. So number of vertices, number of summit here, equals to number of edges, like here, 5 and 5. Same here, V bar 24 and E bar 24, and 24 equals 2 times the total number of edges in the solid. As you know, in the cube, we've got 12 edges. So 2 times 12 equals 24. Or back. Well, of course, you can do it's easier to go from the split net to calculate the different parameters of the solid. And at some point we will see, we'll use a very good example about the football that is, its components are mixed between two shapes, two different polygons. The first one is the hexagon, and the second one is the pentagon. From checking the number of hexagons and number of pentagons, we can deduce all the different parameters for the solid, for all solid. And there is another notion of what I would call the perimeter of the net. So when you flatten a solid, you get perimeter of the net, and we can, for example, measure it by number of edges, external edges. So that this number of external edges that I call a perimeter, it's also equals to V, which is 2 times C. This will be equal to perimeter of all nets, each net. So from here, we see straight away that the number V, like here, it's always even, 2 times C, and the perimeter as well of any net, not only this one, any net, it's always the same, V equals to C. So let me show you the different nets of the cube here. This is just one of the 11. Sorry. So let's Google it. Right. Nets of the cube here. All right. As you can see here, there are 11 different nets of a cube, and we are just taking as an example this cross here in the middle. The other ones, there are 11. The interesting thing about those nets, actually, they are only a part of a larger group of shapes that you can build from 6 squares. Then their name is hexominos, means hexo 6 parts, minos, like dominos and tetraminos. So hexaminos, there are 35 different shapes that you can build with those 6 different squares, but only 11 shapes that make nets for the cube. Right, let's start for this. So we are going to the proof that C equals V minus 1 and P equals F minus 1. So first thing that I noticed back in 1988, that any solid, the number of edges of any solid, it always equals to the number of cutted edges plus the number of non-cutted edges, which is straightforward, obvious. So E, we can write down E equals C plus P. Let's call this first equation. Right. And the second equation just remind me. So I would like to stress that those formulas, maybe they are not very important, but I believe they are little progress in understanding the basics of topology, and also having fun of trying to do those kind of exercises. So this is why I would like to advertise to it, like using the name Euler, which is very famous, through the new Euler's formula, just to attract young people to a very sophisticated science, in actually the field of mathematics, which is topology or graphs theory, or even algebra in general, like groups. Right. So this, for number of total of edges equals number of cutted edges plus number of non-cutted edges, the folds. The second formula that we can write, we can see here when you flatten, when you go from this path, the cube, to its net, and this is just one of the nets, each time you cut an edge, you create one more edge on the net. So, I repeat, this is important. Each time you cut an edge, you create one more edge on the net. So, the number of edges E must be equal to the number of original edges on the solid E plus the number of cuts. Let's call this equation 2. So from those equations, we can straight away inject the value of E in here. So E, little e, becomes C plus P, this is big, capital E plus another C, which is 2C plus P. So E, little e, equals 2 times the cuts plus the number of folds. Let's call this equation 3. So as you can see here, you can already, of course, control and verify here. E here for this net equals 19. Actually, for all nets, you will find that the number for all nets of the cube, they satisfy those. So number of vertices is 14, number of edges 19, and of course number of faces stays the same, 6. So let's check this. E equals 2C plus T. We said that C equals 7 and P equals 5 for the cube. Right? So 2 times 7 plus 5. 14 plus 5 equals 19. So E equals 19. Equals 19. Like just here. Right? Just this is just to control, to verify. Let's prove first that V equals 2C. V equals 2C. Right. As you see, we can, for any polygon like here, for any polygon like here, for example, number of external vertices, let's call it E0 equals to number of edges for any cyclic, for any polygon. So it equals to number of vertices, number of edges, external edges equals number of vertices. Folds P. Okay? So it's better to write it straight away like this. So the number of these edges, external edges, equals number total of edges on the net minus number of folds P, which is also, like we said here, E0 equals V for any polygon equals V. That means, from here, that means E is also equal V plus P. This is equation 4, right? This is equation 4. Look at the equation 3. We've got the same value for E from equation 3.
we write E equals 2C plus P equals V plus P.
We can drop P from both sides and we write V equals 2C.
So we just proved that V equals 2C.
And of course, V equals 2C
and equals E0, which is perimeter. The perimeter of each net. But this is important actually to get the proofs of C equals V minus 1 and P equals F minus 1. Number 5, right?
Okay. Let's go, let's carry on and prove this here. Okay, I can just rub this off to carry on the proof. Right, here as well. I can keep this out like this. So from Euler's 3D, we can write from Euler's 2D, from Euler's 2D in the plane, we've got V minus E plus F equals 1. V, which is here, equals 2C minus E here, E equals 2C plus P plus F equals 1. So 2C minus P plus F minus 1 equals 0. That gives us P equals F, little f minus 1, but little f equals big F. So the number of faces stays the same from the solid to its net.
So therefore P equals F minus 1. Formula 6.
So we just proved that the number of folds, it always equals number of faces minus 1. And now it's very easy to just to inject it here in 3D Euler 3D. Let's carry on here. Okay, here. So V minus E plus F equals 2. So V minus E, as we know from the first formula, from the first equation, that E equals C plus F, here, plus, C plus P, and F, and F equals, from here, we can write that F equals P plus 1, P plus 1, this is F, equals 2. So V minus C minus P plus P plus 1 equals 2. V minus C minus P plus P plus 1 minus 2 equals 0. P goes with P. V minus C minus 1. V minus C minus 1 equals 0. That gives us
C equals V minus 1. Equation 7.
So we just proved that the number of cuts is always equals to number of vertices of the solid minus 1, and the number of folds always equals to number of faces minus 1. There are another different way to prove those results without going through Euler's formulas, using the spanning tree of any Archimedean convex solid, or what you call a net of that, a graph of this solid in general, or any polyhedra, convex Archimedean polyhedra. And that will take a little bit more time, because we need to understand, well, what means a dual graph from a graph, what is a spanning tree, and what is a path in a graph, and also what is a cycle. And from there we can actually bypass Euler's formulas and go straight away to prove that those same results. But this different way is a little bit trickier, because you need already to understand those concepts of graph theory, basic concepts of graph theory. I think it's at the grasps of a high school student, but I believe this way is much easier, because we've got already the main result of topology, which is great from Euler's. And there is a nice thing about this formula. Actually, in 1754, Euler himself was very surprised that nobody else find this before him, and I believe he said it is very surprising that general results of solid geometry, those general results of solid geometry never have been found before, as far as he knows of. He says, I know. Thank you very much. There is another thing that we can just carry on. I want to know that V equals always V bar here, it always equals E bar. And when you go from split net here, each fold creates two other edges. So we can here write that E bar equals E plus P, equals E plus P. E bar equals E plus P. And from those here, as you can see, E equals 2C plus P. So E bar equals 2C plus P plus another P, which is 2 times C plus P. So I hope you can see here. You just rub this off. So yeah, E bar equals E plus P, but E itself equals 2C plus P, so plus P here means 2C plus 2P means 2C plus P, and from the equation 1, E equals, just remind you the equation, recall the equation 1, E equals C plus P. So we've got E bar equals V bar equals 2 times the number of edges on the solid. Here we go. that's it. And this formula is very interesting because we can, for example, go from the football balloon, the football that has got many polygons on its surface. Its components are mostly hexagons and pentagons. So it's easy to enumerate the number of hexagons on the football and the number of pentagons and the number of hexagons, and compute the number of edges. E bar equals V bar. So when you compute the number of edges, you will find there are 180 divided by 2, so you already know the number of edges of the football. And so you have already E, and at the same time you can compute from this formula. From this formula you can compute V, so you go back and you compute V, and from V you get C, because V equals 2C. So from here we can compute, from this step we can compute V, then we compute C, so we know how many cuts. And as we know already number of edges and number of cuts, so we can deduce number of folds, and we can deduce the perimeter of the shape of all the different nets of the football polyhedra, with a nice exercise that could motivate young people to go and study beautiful things in topology or graphs theory, or even